Hi, my name is Aditya and I'm the CEO of Automaski. Today I'm going to be showing you our graph coloring platform called Roma, Hroma, Roma. Now, what is graph coloring? Graph coloring is one of the original complete problems that is very famous. What I have in front of you on the screen is a graph coloring problem. Now, what is a graph? A graph is just a network. It is, there are nodes and they are connected by lines. These lines are called edges, and nodes are connected to each other. They could be uh, uh, uniform in the sense that all nodes will be connected to two or three other nodes, or it could be a non-uniform graph. Now, in a graph, you say you have n nodes and m edges. Now, what is the graph coloring problem? Suppose you have a graph of n nodes and you are told that you can use a maximum of k colors. So this is a k graph coloring problem. Now, you have to color each node using one color such that no adjacent nodes have the same color. If two nodes are connected by an edge, they cannot have the same color. This is the graph coloring problem, and this is NP complete. Now, there are many variants to this, and this problem is difficult but to solve exactly, but uh, it cannot be used in industrial applications just like that. For industrial applications, you need to solve a lot of constraints and other variants of graph coloring. One of the things that you need to do with graph coloring is that you are given a graph of some nodes and edges, and you have to find out what is the minimum number of colors required to color the graph. So obviously the graph will be colorable with, let's say, 20 colors. Can you do with 15? Can you do with 6? Is 6 the lowest number of colors that can have a colored graph? If yes, then 6 is the chromatic number, and this is also NP complete. Now, on my screen, I am going to tell you about all the graph coloring variants that we have implemented in Roma. Now, what I just showed you, graph coloring, is basically called vertex coloring. Basically, the vertices or the nodes need to be colored. If the edges need to be colored and adjacent edges cannot have the same color, then it is called edge coloring. Similarly, there is total coloring of edges and vertices. You color both. There is weighted coloring, fractional coloring, dynamic coloring, online coloring, distance K coloring, list coloring, hypergraph, geometric, and multicoloring. These are all the graph coloring variants that are implemented in Roma. And Roma SDK and the solver platform can also have constraints. For example, you could pre-color. You could assign some nodes or edges colors in advance which cannot be changed during the solving process. There could be constraints on the node colors. For example, node 1 has to have a color which is less than node 2. There could be other distance and bounds based constraints. Now I'll show you. This is the Roma examples SDK, and you just have to install a Python package for Roma, and you can look at all these examples. These are made and these are supposed to exemplify certain things about the SDK, what you can do with it. So you have vertex coloring, edge coloring, total coloring, pre-coloring, list coloring, bounds, order constraints, distance constraints, mix constraints, weighted coloring, fractional coloring, dynamic, online, distance scale, list, hypergraph, geometric, multicoloring, and a benchmark. Now I'm going to show you these examples. So you can simply say Python examples and the name of the example. And there it is. It has done a vertex coloring of a graph with five vertices. This is just to show you. Now, this is not executing on my laptop. This is executing on the server end. And on the server end, we have a hybrid solver. Let me run one another problem of edge coloring. And there you go. A graph with five edges has been colored. Now, we are interested uh, in knowing how large graphs can we color. So I would say we can color graphs of billions of nodes. What does that mean? See, if you have uh, the ability to color 5,000 odd nodes, you would be able to do some spectrum coloring and spectrum assignment, etc. If you have the ability to color 50,000 nodes, then you would have the ability to assign frequencies to telecom towers in India because they are in that range, 3 lakh towers or 50,000 towers per provider or whatever. If you have the ability to color billions of node graphs, then you will be able to lay out transistors on the surface of a microprocessor and so on and so forth. So usually a couple of billions is what you target. I'm going to run a small benchmark with 1 million nodes, and we'll see how it responds. And since the graph cannot be colored with six colors, it should show some messages about violations. Now, this will take around 15-20 seconds. So, let me show you the screen again. It says it's not okay. There are 855 violations, and there are some conflicts, and it is writing down the conflicts. Status is partial. NT is 1 million. Edges elapsed seconds. Now, this is what it does when uh, the problem is theoretically unsolvable or it cannot solve it. Now, why did we create a hybrid architecture? You can easily solve graph coloring problems with hundreds of thousands of nodes with annealers. That is not an issue. But we were targeting multi-billion node graphs. Now, the problem is that this is an NP hard problem, and there is a need to repair the solution after the annealer returns the solution. Let me explain. Just like you polish your shoe, you will get a black coating, but when you finish it with a brush, you get the actual shine. So something like that. And annealer is great at solving a massive problem using energy minimization, but it does have some rough edges, especially at extremely large scales. So what you do is you run a classical time-bound repair process on it, which makes a best effort, to repair the solution, and then it returns. So just like you saw on the screen, it took 28 seconds. This is the solution after the best effort repair process. That is why we have a hybrid solver. Remember, our annealer can solve problems with 100 million variables in seconds. And this hybrid solver sits on top of that and solves graph coloring problems And these are the exact variants it supports. This enables us to solve production grade problems in a wide variety of fields, from chip design to telecom to uh, signal processing, Wi-Fi's, routers, switches, etc. Or even something like scheduling or stuff like that, planning, scheduling, etc. So that's all we had for you today. This is available right away. We've built it over the last 4 or 5 years, so this is not a one-day job, and we are very proud to announce this. Let us know how we can help you out. Thank you very much.